Welcome to this explainer. Okay, today we're diving into, honestly, one of the most fascinating evolutionary leaps in the entire field of AI. In this analysis, we're talking about computer vision. More specifically, the massive race to make object detection not just perfectly accurate, but incredibly fast.
I mean, think about this for just a second. How exactly does a computer go from staring at a completely blind grid of raw, meaningless pixels to instantly identifying, hey, that's a horse right there, and oh, right next to it, there's a rider, right? It's just a staggering jump, going from total mathematical noise to true intelligent recognition. And honestly, the way researchers actually pulled this off, it's nothing short of brilliant.
So here's our roadmap for today. We're going to hit the basics of object detection, look at the jump from slow to fast models, tackle the selective search problem, dive into region proposal networks, break down anchor boxes, and then wrap it all up with a look at YOLO v1.
All right, Section 1. The basics of object detection, and really justifying what our goal is here.
Before we can start turbocharging things, we absolutely have to define our baseline. Now, the foundational goal here is actually surprisingly simple. You've got a single input, right? Just an image. And your system needs to spit out two very specific outputs. First, we need bounding boxes, those crisp mathematical rectangles drawn perfectly around the detected objects. And second, the class labels. This is what identifies what's actually inside that box. Is it a person? Is it a car? Or in this case, a horse? That's the core mission. Everything else we're going to talk about today is really just about doing this faster and better.
Okay, Section 2. Moving from slow to fast and how we sped up RCNN.
So let's talk about the transition from those painful, super clunky computational bottlenecks of the early models to the very first major breakthrough in speed. In the early days, we had what we affectionately, or maybe not so affectionately, call slow RCNN. And it was slow for a really simple reason. It took about 2,000 proposed regions of interest from a single image, and it fed every single one of them through the neural network individually. I mean, think about that. That's 2,000 separate forward passes. It's exhausting just thinking about it. But then came the brilliant leap of fast RCNN. Instead of processing 2,000 separate chunks, the developers were like, hey, why not just run the whole image through the network once? They passed the entire image in to create one unified feature map and then just projected those regions of interest directly onto that flat map. A total game changer.
And to put that into perspective, by extracting features just once instead of 2,000 times, the testing time per image completely plummeted. It dropped from an agonizing 49 seconds down to a mere 2.3 seconds. Like, whoa. Even the training time dropped massively, going from 84 hours down to just 8 hours. It was an absolute revolution. But as we'll see in a second, it still wasn't quite perfect.
Moving on to Section 3, the selective search problem, which was a huge bottleneck. Because despite that massive speedup we just talked about, fast RCNN still had a pretty glaring, critical flaw hiding in its pipeline. The main culprit? An algorithm called selective search. See, fast RCNN was incredibly fast at processing the regions, but it still heavily relied on this clunky external, manual algorithm to tell it where those regions were in the very first place. Selective search was literally the bottleneck holding the whole AI back. It wasn't deep learning, it was really just an old-school algorithm kind of guessing where objects might be. So we desperately needed a system that could learn to find these objects entirely on its own, from end to end.
Which brings us to Section 4, Region Proposal Networks, and finding regions faster.
That urgent need we just talked about, it birthed the ultimate solution. Enter faster RCN and the absolute genius invention of the Region Proposal Network, or RPN for short. Imagine dividing the image into a grid, say a 20 by 15 grid. That gives us 300 distinct little locations. Instead of asking some separate old-school algorithm to guess where objects are, faster RCN uses a small, dedicated neural network that literally slides over the image's feature map. The RPN looks at each of these 300 grid locations and actively hunts for objects. And this dramatically speeds up the process, because everything is now happening right inside the GPU as one continuous smooth tensor operation.
All right, Section 5, Anchor Boxes and Intersection, and how we evaluate these shapes.
Now you might be wondering, how exactly does this network know what to look for at each of those 300 grid points? Well, think of it like handing the AI a cheat sheet. Instead of forcing the network to learn how to draw a box from absolute scratch, which is super hard, we place predefined shapes, called anchor boxes, at every single grid point. The network then basically does a quick binary classification. Is there an object here? Yes or no. If the answer is yes, it calculates exactly how much to adjust or transform that anchor box to perfectly fit the object. Finally, it uses some clever math, a filter called intersection over union, or IOU. Basically, if the proposed box overlaps with the actual ground truth by more than 0.7, so 70%, it keeps it. If not, it just tosses that bad guess right out the window.
And finally, Section 6, a look at YOLO v1. You only look once.
So faster RCNN was absolutely amazing, no doubt. But some researchers thought, hey, we can go even simpler and even faster. Enter YOLO v1, which literally stands for You Only Look Once, and it is a real game changer. YOLO basically takes that complex, multi-stage pipeline we just discussed and throws it entirely in the trash. It unifies the whole shebang, finding regions, evaluating anchors, predicting classes, into a single, elegant, convolutional network pipeline. You literally just feed the image in once, and the network outputs a 3D prediction map containing all the bounding boxes and class probabilities simultaneously. It took everything we've learned and applied it with unprecedented, real-time efficiency.
And this really grounds everything we've been talking about. By combining that visual grid with some localized calculus, the neural network essentially nudges the width, the height, and the center coordinates of that box until it perfectly captures the object. It is literally pure math creating visual intelligence. It completely ties all that abstract tensor math and those deep learning loss computations directly back to the visual reality we see with our own eyes.
Which leaves us with this final thought. I mean, we have gone from an agonizing 49 seconds in image down to 2 seconds and then down to mere milliseconds with YOLO. So how will these micro-optimizations, these brilliant little ideas like anchor boxes and unify pipelines, continue to pave the way for real-time, zero-latency video processing? Think about technologies like self-driving cars or even robotic surgery. The evolution from blind pixels to intelligent, split-second recognition is already completely reshaping our world. Thanks so much for joining me on this explainer today. And as always, keep questioning the technology around you.